Hello, science fans! Today, we're diving into a world that sounds like it's straight out of a science fiction movie, the world of metamaterials. These aren't your everyday materials like wood or plastic. Oh no. Metamaterials are special, engineered materials designed to have properties not found in nature. Imagine a material that can bend light around an object, making it seem invisible, or one that can absorb sound perfectly. That's the kind of radical stuff we're talking about. These materials get their amazing abilities not from what they're made of, but from how they're put together in tiny, intricate patterns. It's all about structure, people. For a long time, making these incredible materials was super difficult and expensive. Scientists had to build them piece by tiny piece in a lab, which took ages. You couldn't exactly make an invisibility cloak for an airplane if it took you a year to make a piece the size of your fingernail. But guess what? That's all changing. Researchers are now developing brand new ways to cook up these materials much more easily and on a much larger scale. We're talking about revolutionary manufacturing methods that are making the impossible possible. This is a huge deal for the future of technology, from faster computers to better medical devices. Think of it like this. We used to build with big, clunky bricks, but now we're learning to build with microscopic Lego blocks that can do extraordinary things. These new techniques are like getting a brand new, super advanced recipe book for the future. Instead of just following old instructions, we're inventing entirely new ways to mix our ingredients. We're going to explore some of these exciting new methods, like using super small particles, special frozen mixtures, and even a process that works like a giant newspaper printer. So, put on your safety goggles, because science is getting seriously cool, and we're about to see how it all works. These new ways of making metamaterials are not just a small step forward. They are a giant leap for material science. By figuring out how to produce these complex structures more efficiently, we are unlocking their potential to solve real-world problems. We're moving them out of the laboratory and into our lives. From communications to energy, the impact could be enormous. The ability to control light, sound, and heat in ways we never could before opens up a whole new toolbox for engineers and inventors. It all starts with how we make them. So let's get into the nitty-gritty of these awesome new manufacturing tricks. So, how do you build something with properties that nature forgot to invent? You start small. Very, very small. I'm talking about nanoparticles. A nanoparticle is a tiny particle of matter that is between 1 and 100 nanometers in diameter. To give you some perspective, a single human hair is about 80,000 nanometers wide. So these things are incredibly tiny. But don't let their size fool you. When you get down to this nanoscale, the rules of physics can change in fascinating ways. Materials can have different properties at the nanoscale than they do when they're in a big chunk. It's a whole new ballgame down there. Scientists are now using these nanoparticles as the fundamental building blocks for metamaterials. Think of them as custom-designed atoms. By arranging different types of nanoparticles, like tiny spheres of gold or silver, in a very specific repeating pattern, we can create a larger material that interacts with light in a unique way. We can make a material that reflects only a certain color of light, or one that absorbs light with incredible efficiency. This process is often called bottom-up manufacturing, because we are building a complex structure from the bottom, starting with the smallest possible parts. It's precision engineering on a mind-bogglingly small scale. For example, imagine you want to create a material for an ultra-thin camera lens. You could arrange nanoparticles in a precise flat layer. The specific size, shape, and spacing of these nanoparticles would determine how they bend light. By carefully controlling this arrangement, scientists can create a metasurface that focuses light just like a thick, curved glass lens, but it's thousands of times thinner. This is possible because the nanoparticles work together as a system, creating a collective effect that is greater than the sum of its parts. Each tiny particle plays its part in manipulating the light waves passing through. This nanoparticle assembly method is revolutionizing optics and electronics. Previously, creating these patterns was painstakingly slow. Now, scientists are developing ways to get the nanoparticles to assemble themselves. By placing them in a liquid and controlling the conditions, the particles can be coaxed into forming the perfect crystal-like structure all on their own. This is called self-assembly, and it's a game changer. It allows us to create large areas of perfectly structured metamaterials much more quickly and cheaply, paving the way for new types of sensors, displays, and even energy harvesting devices. It's a big future for some very, very small things. Alright, let's talk about another brilliant method for making metamaterials. This one involves something called eutectics. Now, that's a big word, but the idea is pretty simple. A eutectic is a special mixture of two or more substances that melts and freezes at a single super low temperature, lower than the melting point of any of the individual ingredients. Think of how salt melts ice on the road in winter. Salt and water form a eutectic mixture that freezes at a lower temperature than pure water. Scientists are using the same principle, but with much more exotic materials to build incredible microstructures. Here's how it works for metamaterials. Scientists take a mixture of, say, a ceramic material and a metal, and they heat it up until it's a completely uniform liquid. Then, they cool it down very, very carefully. As the liquid mixture solidifies, something amazing happens. The two materials don't just clump together randomly. Instead, they separate out and freeze into a highly ordered, intricate pattern. Depending on the materials used and how quickly they are cooled, they can form amazing shapes, like perfectly parallel rods of one material embedded within a matrix of the other, or complex web-like patterns. The real magic is that we can control these patterns. By changing the composition of the mix or the speed of cooling, scientists can tailor the final structure. They can create a material with millions of tiny, aligned metallic nanowires running through it. These nanowires can act like antennas, allowing the material to interact with light or other electromagnetic waves in a very specific way. For example, a material like this could be designed to be transparent to visible light but completely block infrared radiation or heat. This makes eutectics a powerful tool for creating a whole class of optical metamaterials. This method is fantastic because it allows nature to do most of the hard work. Instead of placing each tiny rod one by one, we let the fundamental laws of thermodynamics and crystallization build the structure for us. It's a form of self-organization, just like with nanoparticles. This process allows for the creation of large, three-dimensional metamaterials with incredibly fine details. These materials could be used in thermal management for electronics, to create better lenses, or even in shielding applications. It's a wonderfully clever way to use chemistry and physics to build the materials of tomorrow, one frozen mixture at a time. So we have these fantastic ways to design metamaterials using nanoparticles and eutectics. But what if you need a lot of it? What if you want to cover a large area like a window or the wing of an airplane? Building it bit by bit in a lab won't work. For that, we need to think big. We need to think like a factory. And that's where a process called roll-to-roll manufacturing comes in. If you've ever seen a newspaper being printed, you've seen the basic idea. Huge rolls of paper fly through a machine, getting printed on at incredible speeds. Now imagine doing that, but instead of printing with ink, you're printing metamaterials. Roll-to-roll processing adapts this high-speed, high-volume concept for manufacturing advanced materials. It involves taking a flexible base material, like a sheet of plastic or thin metal foil, and running it through a series of rollers. At different stages, the machine can deposit, etch, or print microscopic patterns onto the surface of the material. It's like an assembly line for metamaterials, creating vast sheets of them continuously. This is how we can take a technology from a lab curiosity to a mass-produced product. This method is a huge breakthrough because it combines speed with precision. The printing techniques used are incredibly advanced. They can create features that are nanometers in size, which is exactly what we need for metamaterials that manipulate light and other waves. This process can be used to create flexible metasurfaces, which could be applied like a sticker to windows to block heat, or to screens to direct light for a brighter display. The ability to make these materials on large, flexible sheets opens up applications we could only dream of before. Think of smart fabrics, flexible electronics, or even wallpaper that can enhance Wi-Fi signals in a room. By bringing the cost down and ramping up the production volume, roll-to-roll processing is the key to making metamaterial technology truly accessible and widespread. It bridges the gap between scientific discovery and real-world application. The development of these new manufacturing methods, from self-assembling nanoparticles to eutectic solidification and large-scale roll-to-roll printing, is just as important as the discovery of the metamaterials themselves. Together, they are accelerating a technological revolution. We are learning not just what to build, but how to build it efficiently. And that, my friends, is going to change the world. Consider yourselves informed.